It's often the case that when you're applying probability, you're applying it sometimes, like for insurance companies, if you're an actuary, to situations where bad things happen, right? Fires, car accidents, hurricanes, people die from natural causes if you work with life insurance. In fact, it used to be the case that, like with life insurance, well, they didn't have the death rates were talked about it as death rates, and they had what are called mortality tables, but that was all a little bit too morbid, and they've changed the terminology. They call it life insurance now. They also call it life tables instead of mortality tables. So they try to make a positive spin on it. But yeah, this prob number 5 that you had here about deadly radiation is not so pleasant to think about. People are being exposed and dying with related to nuclear accidents. I should say, by the way, that nuclear power plants are actually very safe these days. So it's pretty rare for a nuclear accident to happen. Anyway, LD50 is a level of exposure to radiation at which 50% of people eventually die. How quick? It doesn't say. We're assuming there's a nuclear accident and that 30% of the workers at the plant are exposed to that level of radiation and die. Key word there, and, right? We talked about and versus or, intersection versus union last time. That's one thing you want to look for, is those kind of keywords. 40% die. Some are exposed to radiation, maybe some that are not, perhaps. And then 68% are exposed to that level of radiation, or they die. They're either exposed to the radiation or they die, or both. The or is always assumed to be an inclusive or. We want to answer a few questions. What is the probability that a randomly selected worker is exposed to that level of radiation? And ultimately find the probability that a randomly selected worker is not exposed to LD50, that level of radiation, but dies. They die anyway. They're probably still exposed to some level of radiation, just not the higher level. This is saying they're not exposed. It's like it's LD prime, the complement of LD. But die really means and die. So sometimes the and is kind of hidden. The but here really implies not exposed and they die anyway. Kind of the but is just for emphasis. So all that goes into the problem solving. Let's go ahead and take these numbers and put them into a Venn diagram. So this is your sample space. You can think of the sample space in this case as representing all the people, all the workers at the power plant. Some number of them are exposed to LD50. I'll just call it LD for short. That blob represents, again, probably everybody who's there that day is exposed to some level of radiation. The question is, are they exposed to this LD50 level, meaning high enough that half the people would be expected to die? It's not everybody. You got the proportion of people who die as well, just call that D. The first bit of information was that 30% are exposed and die. And intersection, that's what goes in there. Symbolically, the probability that a randomly chosen worker was exposed to the high level of radiation and dies is 0.3. The next bit of information was that 40% of people die. The probability of D is 0.4. If 40% of the people at the plant die, that's interpreted as a probability. The probability that a randomly chosen worker from the plant ended up dying is 0.4. If you're trying to assess the chances and you don't know ahead of time whether they died or not. That number should not be labeled there, because when you label these different regions in the Venn diagram, it should be, well, what goes there should just correspond to this crescent shape, meaning the people who died but were not exposed to the LD50. So whatever goes here, you want it to add to 0.3 to get 0.4, and therefore it must be 0.1. This could be thought of as, if you like, the probability of LD intersect D plus the probability of LD prime intersect D. That's what I just used. And this is 0.3 plus question mark, and therefore question mark is 0.1. That's a formal symbolic way of doing what was much easier to think about with the Venn diagram, right? It's much easier to kind of make a mistake when you're writing this kind of stuff. I mean, you should practice that anyway to understand. What did I use there in writing that equation? I used axiom 3, the addition rule for mutually exclusive events. Right? These two sets, LD intersect D is this one. LD prime intersect D is this one, this crescent shape. They're mutually exclusive, no overlap. Their intersection is empty. D is the union of the two. So the probability of D can be written as a sum of those two probabilities. We know this one is 0.3. We didn't know that one, but we can easily find it now. Next bit of information is that 68% of workers are exposed to LD50 or die. And again, or, unless said otherwise, is always an inclusive or. One or the other or both. 68%. P of LD union corresponds to or is 0.68. Looking at the diagrams much easier than thinking about equations. You want the sum of the numbers here, here, and here to be 0.68. 0.3 plus 0.1 plus, I'll call it double question mark for what goes there. So double question mark is going to be 0.68 minus 0.4, 0.28. That's what goes there. It's good to fill in the diagram completely. All the probabilities need to add to one of these 4 mutually exclusive events, including outside LD and D together. These together add up to 0.68. We already knew that. Therefore, out here, it's 1 minus 0.68, 0.32, are neither exposed to that high level of radiation nor die. So you can say that as neither nor. You could also say they're not exposed to that high level of radiation and they did not die. Different ways of phrasing things. We're asked, what is the probability that a randomly selected worker is exposed to the LD50? Okay, that's in here. It's good enough based on the diagram to just go ahead and write that as 0.28 plus 0.3 is 0.58. That's the answer to the first question. Could you write this as axiom 3 in terms of probability? Sure, you could write this is P of LD intersect D prime, actually, that's the 0.28. That's outside D. Complement of D plus P of LD intersect D. These again are mutually exclusive events because one's got a D prime and one's got a D and intersection. And you can see it in the picture. These are two non-overlapping sets. Their intersection is empty. And the second question is, find the probability that a randomly selected worker is not exposed to LD50 but dies. Not exposed but dies really is an and. That's the implication. They were not exposed to the high level radiation and they did not die. Phrased as exposed but did not die. They're not exposed, I meant to say, but they did die. Again, you can look in the diagram. Not in LD, but in D. That's the 0.1. And I think it's good enough for me both on homework and on tests for this kind of problem to just draw the diagram. I mean, if I asked you to write equations like this, you technically should be able to, but that's not really something I focus on. In the pressure of an exam, it's just a bit too much to expect you to write things like this, I think. So that's why the Venn diagram is such a good tool. And I think it's clearer as well. I think it's problem 14 or something, you end up thinking about conditional probabilities in this context. We'll go ahead and look at that one. These are about conditional probabilities. What is the probability? You don't see the word conditional here, so you have to understand why it's conditional. What is the probability that a randomly selected worker will die given that? Okay, look for words like given that, or if it is known that, or if you assume that. If it's given that he is exposed to a lethal dose of radiation, probability that they die, probability that the random worker dies, given that they're exposed to a lethal dose. Understand this notation. Every time you see this, it's a conditional probability. Probability of the first thing, given that the second thing has been assumed to occur. We can write the formula. Here it is. And we'll go ahead and use it, but we should also think about why the formula makes sense. The formula says, do the ratio of the probability of D intersect LD, the 0.3, divided by the probability of LD, the sum of those 2.58, which is about, well, it's close to 50%. That's why it's called LD50. Not exactly 50%. About 0.517. You shouldn't expect it to be match the 50% exactly, because this effectively is a sample. You know, it's one power plant. It should be close to 50%, but not necessarily exactly 50%. This is the chances that you die if you're exposed to a level of radiation at which 50% of people die. And based on this one power plant, that probability is slightly higher than 0.5. Why does this formula make sense, though? It's like we've restricted the sample space. We're assuming they've been exposed to that level of radiation. Our sample space, based on that assumption, has shrunk to just the LD circle. Effectively, what proportion of people in that circle die? If you imagine these probabilities as being corresponding to people, maybe there's 100 people who work in the plant, the 0.3 is like 30 people, and the 0.28 is like 28 people. 30 out of 58 people died. So because of that line of thinking, it's supposed to be intuitive. Make sense? I don't know if it's asked for, but let's see. Well, okay, let's also talk about the complement of this. What's the probability that they do not die, given that they are exposed to a lethal dose of radiation for at least 50% of people? I hope it's intuitive that it should be 1 minus this answer. Is it? If we use the formula, still have a 0.58 in the bottom. Go back up here. We're in D prime, but it's still an LD. It's the 0.28 up on top. And those two fractions do add up to 1, right? They have the same denominator. You would add the numerators, 0.3 plus 0.28 is 0.58. You get 0.58 over 0.58 or 1. And yes, if you approximate this in your calculator, we should get 0.483. Let's see if we do. 0.483 when you round. One minus 0.517. we should not expect this answer to be the same as, well, this probability to be the same as this probability. This probability here could be something completely different. I switched around the roles of the D and the LD to go down here. Now I'm saying, oh, there's a person who died. I wonder what are the chances that they were exposed to that level of radiation. The numerator is still the same. I'll write the D and the LD in the opposite order, but that doesn't matter for an intersection. It's the denominator that's different. We're looking at the people who died instead of the people who were exposed to the high level of radiation. In this context, we've shrunk the sample space to this blob here. What proportion of those people were exposed? Pretend these probabilities are multiplied by 100. It's like 30 out of 40 people. Oops. Yeah, okay, the bottom shrunk. Wait a minute. Yeah, 0.3 divided by 0.4. I was looking there. I meant to look up there. 0.3 divided by 0.4, 0.75. 3/4, 75% chance. Mentioned the other day that you could try to think about these things more intuitively, perhaps by thinking about areas of the diagram. That's hardly ever done because it just takes too much time. But if you wanted to think about these things more intuitively that way, you could. I am going to do a problem today where I do think of it that way, and it's going to be really helpful.